welcome to this explainer. Today, we're diving into something you probably have sitting right next to you or maybe even in your ears right now. We're talking about one of the most densely packed pieces of engineering most of us own, the modern earbud. We're going to break down the absolutely incredible manufacturing process that takes just a few basic raw materials and turns them into the high-fidelity acoustic engines we rely on every single day. Let's get right into it.
Seriously, have you ever stopped to wonder what's actually inside those little earbuds? I mean, it's so easy to just pop them in, press play, and completely forget about the hardware doing all the heavy lifting. But the hidden science, the intricate design, and the sheer innovation packed into these tiny devices, it's literally a masterclass in miniaturization. By the end of our deep dive today, you're going to have a whole new appreciation for the complex acoustics happening right there inside your ear.
Okay, let's dive into this. Phase 1, the raw materials.
Every great piece of hardware starts from the ground up with some highly specialized raw materials. First off, we've got engineered high-density plastics. These have to be extremely lightweight but tough enough to protect the delicate stuff inside. Then we have the copper wiring. This isn't just any wire. It's specifically routed to transfer high-bandwidth electronic data with zero audio degradation. And finally, the magnets. Now, we aren't talking about your standard fridge magnets here. We're talking about incredibly powerful neodymium magnets, which are absolutely crucial for generating the electromagnetic fields we need for high-fidelity sound.
You can really think of the sound driver as the beating heart of your earbuds, and it relies heavily on those neodymium magnets we just talked about. Here's how it works. When an electrical audio signal passes through a tiny voice coil suspended inside that magnetic field, the coil rapidly pushes and pulls against a microscopic diaphragm. That movement actually displaces the air, generating the exact physical vibrations that eventually hit your eardrum. Without this precise electromechanical reaction, total silence. It's like a tiny, invisible drum constantly beating to the rhythm of your music.
Moving right along, we hit Phase 2, precision assembly inside. Now, this is where things get really mind-blowing. We're packing a staggering amount of processing power into a space literally no bigger than your fingernail. At the core is essentially a system on a chip, or SoC. Think of this as the brain of the operation, handling complex wireless protocols to keep your Bluetooth connected without any annoying lag. Right next to that, you've got highly efficient power management chips, just sipping electricity from microscopic batteries to keep your music playing as long as possible. And layered right on top of all of that, capacitive touch arrays that instantly register when you tap to pause or skip a track. Everything is placed with absolute surgical accuracy.
Which brings us to Phase 3, designing for comfort.
Here's a fun fact. Human ear shapes are just as diverse as fingerprints. Every single one is completely unique. So to bridge the gap between all that rigid hardware we just looked at and our delicate human anatomy, engineers use highly adaptable molded silicone tips. It's honestly such an elegant solution to a massive ergonomic problem. How do you create one mass-manufactured product that can conform to and comfortably fit millions of totally unique ear canals? Well, soft silicone is the answer.
And that simple little silicone tip, it actually serves a brilliant dual purpose. First up, it creates a physical acoustic seal. This gives you crucial passive noise isolation by physically blocking out the noisy world around you. But at the exact same time, the silicone material distributes pressure evenly inside your ear. That means less fatigue and way more long-wear comfort. It lets you listen for hours on end without feeling any of those sharp, rigid electronic components hiding just underneath.
Up next is Phase 4, rigorous global testing.
Before a single pair of earbuds is allowed to leave the manufacturing facility, they have to run an absolute gauntlet of demanding quality control checks. We're talking strict engineering tolerances here. For sound quality, highly calibrated microphones analyze the frequency responses to make sure the crisp highs and deep lows perfectly match the intended acoustic profile. For durability, they put these things through the ringer: thermal shock, drop simulations, moisture exposure, just to guarantee they can survive your everyday life. And finally, the power consumption is stress tested to make sure those internal microbatteries maintain peak performance over their entire lifespan.
And finally, we arrive at Phase 5, a pocket-sized marvel. Ultimately, this whole process is a beautifully seamless blend of physics, electronics, and pure innovation. It's so fascinating when you really step back and break it down, right? The complex physics of those magnetic voice coils, the microscopic processing power of the silicon chips, and the thoughtful ergonomic design tying the whole shebang together. It really changes how you look at these things. They aren't just pieces of plastic, they are true modern engineering triumphs. The journey from basic, cold, industrial materials like copper wiring and raw silicon, all the way through precision microassembly and rigorous tolerance testing is what gives us the refined, high-fidelity sound we get to enjoy every single day. It's an incredibly elegant manufacturing arc, carefully designed to seamlessly weave advanced acoustic technology right into the fabric of our daily routines.
So, here's a question to leave you with. Next time you press play, will you just hear the music, or will you hear the marvel of modern engineering whispering in your ear? Taking a second to appreciate the absolute sheer density of tech we carry around in our pockets every day, well, I think it makes the world a whole lot more fascinating. Thanks so much for joining me on this explainer, and I'll catch you next time.